Welcome to the Control Engineering Webcast, Best Practices for Effective Automation Applications, sponsored by Maverick Technologies, Mitsubishi Electric, and Schneider Electric. I'm your moderator, Mark Hosky, and I'm happy to join you today on behalf of Control Engineering and CFE Media and Technology. CFE Media has met the standards and requirements of the Registered Continuing Education Program. Credit earned on completion of the program will be reported to RCEP at rcep.net. A certificate of completion will be issued to each participant. As such, it does not include content that may be deemed or construed to be an approval or endorsement by RCEP. So here's the course description. No matter what automation technologies are being considered or applied, universal rules apply to automation technology projects. Whether just starting or a seasoned expert, this advice can help when applying automation. Automation can do quite a bit, but you should not overreach automation's capabilities. It cannot cure overly complex operations. Get the design first, then apply the right automation. Real-world examples in this webcast will help fill the skills gap with smart manufacturing. Learning objectives for this course are to assess the process or processes under consideration for automation, determine if a redesign is needed prior to automating, consider key ways automation can influence and enhance process design, identify steps for an automation implementation, and examine lessons learned and best practices for effective automation applications. To get the best results from the webcast platform, please note the following. If you have technical problems, click on the question mark at the top right corner of the screen to bring up a list of system checks if you have technical problems before escalating to an online technician. If you're experiencing issues with the slide or audio, please refresh the browser or click the Refresh Media button directly under the presenter's headshot. You can control the volume settings of the webcast by adjusting the volume on your computer or the volume on the webcast platform. If you need a technician, type a message into the Ask a Question box and someone will get to you as quickly as possible. Answers to the technical questions will be in the Answered Questions box on the left side of the screen. You can also use the Ask a Question box on the left side of the screen to type questions for the speakers during the presentation for the Q&A session at the end. You may ask questions at any time during the presentation, and we'll get to as many as time allows with verbal answers during the Q&A session at the end. To download the presentation slides, use the Event Resources area on the left side of the screen. Expand the presentation screen size by using the arrow on the upper right. To take the Learning Unit exam, use the Learning Unit Exam tab option at the top of the screen. The exam will open in a new browser. You can complete the exam after the webcast, but the link will break when the webcast signs off. So if you intend on taking the exam, you might want to open that beforehand. The exam will be posted on the on-demand version of the webcast. The exam is for 1 RCEP ACEC Certified Professional Development Hour. The webcast is being recorded, including the Q&A session. We'll post the archive on the Control Engineering website in a few days, and we'll send you an email with the link to the archive when it's ready. The method of delivery and category. This event is a live educational webcast presented on August 16th, 2022. The educational category is technical, health, and safety. So now here we'll pause for a word from our sponsors. Please stay tuned. After the video, there might be a short pause to compensate for varying internet speeds.
TSN, which stands for Time-Sensitive Networking, is truly a game-changing technology for really moving data from factory floor devices into the industrial Ethernet through IoT devices and pushing that data into the cloud.
Make it for exhilaration, for reconnecting, for endorphins. The industries of the future mean being truly open, so you can make what you make with the next generation in mind, employing resilient operations and redefining the role sustainability plays in industry. We'll help you make it better, so you can make it for life.
I'm so pleased to introduce today's distinguished speakers, Chris Clayton and Kevin Tom. Each submitted an article for the August Control Engineering issue on applying automation topic, and we'll provide those links at the end. A little more on each presenter. Chris Clayton is an advanced manufacturing engineer for Applied Manufacturing Technologies. He specializes in automation consulting, 3D simulation and animation, and sales proposal support. He's worked for AMT clients in a variety of industries, including aerospace and automotive. He's also supported customers navigating the complex transition from manual processing to automation for products ranging from gelatin and pudding to fire trucks and grain trailers. Kevin Tom is the lead automation engineer at Banks Integration, an E-Tech Group company. He specializes in process control system design, implementation, testing, and validation. He primarily works in the highly regulated life science industries, applying his attention to details and adherence to good manufacturing practices. He holds a degree in biochemical engineering from University of California, Davis. I'm Mark Hosky, Control Engineering, covering automation, controls, and instrumentation since 1994. I have a Bachelor's of Science degree in journalism, and I've been writing and editing since 1982, and I've been writing about technology since 1987. Next, we want to know a little bit more about you. And so here, for the audience listening live, please participate in this poll. The question is, what are leading considerations for automating? You can select three, your top three results. So eliminate tasks that are dull, dirty, dangerous, the environmental health and safety issues, process and or asset optimization, more quality, less waste, more throughput, free up available humans for other things and attract more applicants, enable remote monitoring, predictive or prescriptive maintenance, Industry 4.0, Industrial Internet of Things, smart manufacturing initiatives, sustainability initiatives, real-time analytics for better business decisions, part of process workflow redesign or budget process, next step after R&D pilot projects, or enable more frequent updates with interoperable standards. So let's see how the poll is doing. Wow, look at that. Okay, so we have about 25%. The highest one would be choice B, process and or asset optimization for more quality, less waste, and more throughput. The second highest, tied for second, is the first choice, eliminate tasks that are dull, dirty, and dangerous, and D, which is enable remote monitoring and predictive or prescriptive maintenance. So that allows us to get a little more feedback from our audience. And now we can get on with the presentation. Thank you very much for participating in that poll. So Chris, would you like to please go ahead?
Thanks, Mark. And thank you to Control Engineering for having me today. As Mark mentioned, I am an advanced manufacturing engineer at AMT. And one of my main roles is consulting with clients who are considering automation. Now, often these are companies that are running a predominantly manual process. And are just now dipping their toes into the automation world. So as part of my job, I am frequently asked whether a process is a good candidate for automation. And really, from my perspective, the only logical place to start answering that question is with data. One of my favorite quotes is by W. Edwards Deming. He was an American engineer. He had a profound impact on Japanese manufacturing back in the 1950s. So the quote is, without data, you're just another person with an opinion. Now, anybody on the call who's worked in a team or a group project knows that everybody and anybody has an opinion or a suggestion about the best way to get things done. Now, the problem that becomes from that is the question, whose opinion is the best? Now, is it possible to have a system to help us get to the best answer? How can we apply an objective measurement tool to a group of subjective opinions? So the next few slides is going to follow a process of data collection and data analysis that's really geared towards turning those opinions into solutions. Ultimately, recommending an automation solution should be a data-driven process. If we start from a solid base of data and force the decision-making process to consider that data throughout the assessment period, it often makes it very clear if automation is a wise investment or not. So what kind of data are we talking about here? Honestly, from my perspective, all of it. The more, the better. Now, I'm only half joking, but again, as Mark mentioned, I've helped clients in a lot of different industries: aerospace, hydroponics, grain trailers. I'm not an expert in any of those industries. Our clients and our customers are. So part of the assessment process is what I like to call drinking from a fire hose. It usually involves learning more about the process of making things than I ever thought I'd learn. And really the goal there is to try to learn as much about a customer's process and product as possible in order to identify the best potential applications for automation. This typically requires a facility visit, a few days, keyed completely around data collection. It means collecting days of video, talking to everybody from production managers to maintenance technicians, operators and engineers. We pull in sales, IT, safety teams. We get our hands dirty. We touch the product. We go through the process ourselves. And again, the main goal is to understand as completely as possible our customer's perspective in order to get a better, give better support to our recommendations in the future. So the more thorough we are in the data collection stage, the less surprises we have later, and the more confidence the customer or client has in the process. So again, the main areas of data we're looking at, obviously, this is usually in a manufacturing space. So product is the number one piece of data that we're out there looking for. What are they making? What's the historical production data, the part mix, part drawings, 3D models, dimensions, weights? Again, we're looking for anything and everything because we don't know what's going to necessarily be important later on down the line. The next thing we're looking at is process. How's the customer currently making their parts? This involves anything from process flow maps, work instructions, the paperwork and the data that flows through the entire process. And the next area is equipment. What are the tools being used to make the parts? Again, if you look at the industries in general, there's a lot of custom machinery, custom tools out there. We're looking for spec sheets, drawings, models. What are the preferred OEMs that the customer client prefers working with? And again, all of this equipment, the process has to happen in a physical space. It's important to know our sandbox. What is the facility and layout information? Is our space constrained at all? Is the customer willing to break new ground? Is it a greenfield? Are we ripping and replacing equipment or moving equipment around? And a lot of the information we're receiving in this category is required in order to pinpoint potential facility modifications. Do we need to pour new concrete slabs to handle heavier machinery or equipment? Where are the columns at? Another big thing that is always bite you later down the line if you don't have that information first thing. Another major category is labor. How many current operators are being used? What's the shift schedule? What does the labor pool look like in the area that the facility is located at? Is it union or non-union? What's the goal when it comes to labor? Are we trying to replace skilled labor with unskilled labor? Are we trying to bridge a labor shortage gap? And what does the desired labor situation look like from the business perspective? Which leads me to the last category that I handily wrapped up in business. It's basically everything else. This usually comes in the form of high-level goals or target setting, where we're looking at it from an overall business perspective. What is the main goal of an automation project in the first place? Is the customer looking to increase throughput? Are they looking to increase quality, reduce labor? What are their ROI and payback requirements? Is it a 2-year, 3-year payback? And then, the really important one when it comes to buying the automation is what are our capital expenditure limits? Again, the goals in this data collection phase are really to tease out what is important to the customer. And we want all the stakeholders to agree on what the goals, the targets, the KPIs are in order to gauge whether that automation is a success down the line. So data collection, again, facility visit. While we're there at the facility, some of the potential candidates for automation can be easily uncovered. Typically these are known as the low-hanging fruit. And typically, traditionally, and I'm sure a lot of people on this call have heard it before, sometimes it's the 3Ds, 4Ds, 5Ds. Any of the processes or tasks that you're looking at that fall into one of these or more of these categories typically can make a good case for automation. So we're talking dull, dirty, dangerous, difficult, and dear. So what do we mean by these? A dull process, process that's repetitive or boring. Anybody that's worked on an assembly line, perhaps, that is doing the same task over and over again. An operator who is not engaged will frequently make mistakes, and quality tends to suffer. Is the task dirty? Is the process or the environment hazardous? Things we're talking about here, welding, painting. A lot of these tasks have been successfully replaced with automation. Dangerous tasks, again, if the task is going to potentially cause harm to a human operator, heavy loads, sharp parts, environments that contain hazardous gases. Again, great automations or great potential applications for automation. Difficult. Is the process hard for a human operator to execute? Again, we're talking small parts or heavy parts, awkward parts, things that are hard to assemble, tight spaces, excessive walking or energy required. Great applications for automation again. And then the last one, dear. Is the process or the part critical, or is it expensive? Tight tolerances can usually be more repeatable using robotics or other automation. And also the cost of a botched part due to human error, something that a lot of companies are looking to avoid. So investing in automation seems to make sense for that particular D. So at this point, we've collected all the data. While we were on site, we identified potential low-hanging fruit for applications for automation. What do we do now? Now it's time to start analyzing all that data we received. Anybody on this call who's had the task of data analysis handed to them knows that this could potentially turn into an all-out mess. Depending on the quality of data, the missing pieces of data that you don't have, this could definitely take some significant time and energy. It also takes some intuition and some experience to know what you're looking for. So at this stage, we're taking our product data and we're breaking out a product mix. We're putting things into product or process families. We're identifying rates and dimensions and weights. really what we're trying to do here is get a handle on how the product is made, and could it be made or processed with automation. At the same time, we're collecting all of the requirements and parameters that are going to support our automation decisions further on in this process. So a simple example here is you need to know the dimensions or the weight of your product in order to know what conveyors or robots can handle that product. So again, that's a very simple example, but we're trying to create a framework that will allow us to make objective decisions and recommendations later. So we're identifying some SKUs that may be problem parts. They may be more difficult to make. They may differ significantly from the rest of the products that customer is making. Those are all going to speak to the automation solutions in the next step of brainstorming and concept design. So again, we're creating process flow maps, identifying inefficiencies in the current process flow so that those don't make it into the automation. So again, all the steps in this data analysis stage should be with the goal of defining requirements, setting up the parameters, and creating a decision-making framework for the next steps in the assessment process. So at this point, we can usually take a look at our product mix. We should have that data, and we can ask what I like to call a reality check question. So at AMT, we have what I refer to as our own version of the Pareto principle. And that's a rule of thumb that we typically use, that it usually only makes sense if 80% of the customer's product mix can be captured and automated. Anything less than that requires a much healthier business case. And usually the remaining 20% or less can be pushed to some sort of manual or semi-automatic solution, something that can handle maybe a lower throughput or rate. Traditionally, this meant that a chaotic product mix or a high variation, low volume product mix, we'd struggle to make a case for all that, for the automation for that. The complexity of the required automation would price out most customers. However, recently, and in my experience, the math can often be much simpler than this, and usually starker. And what I mean by that is frequently the question isn't whether automation makes a good business case. It's more of an existential question: is do we automate or do we die? And there are a few reasons why a company would be asking themselves that question. So some clients that we've come across are in what I'd call a labor desert. Towns with a couple of thousand people that don't typically offer a constant pool of labor resources. If the task at hand falls into one of those 5 Ds, you're going to find labor that's not really willing to do that anymore. Sometimes a bigger player enters the market. There's a big, warehouse that moves in down the street and starts to siphon off the labor pool, and suddenly you're shorthanded. And again, it can be hard to convince workers to work in one of those 5D environments when they could potentially make more down the road at a desk job. Another common story is that a small company, suddenly finds its product in high demand. Suddenly they need to go from a mom and pop shop to a manufacturing powerhouse. So in order to make parts or more parts, the natural solution is to hire more people. Again, that's not always possible. So automation is required to fill that gap. And lastly, if a close competitor of yours has made that automation leap, sometimes the only solution is to do so yourself in order to keep up. So at this step, we're kind of getting into the trying to figure out if we need to redesign the part prior to automating. At this point, we're analyzing the process for inefficiencies. The main thing we don't want to do is automate a bad process. Again, a pretty simple math calculation here. Automating a bad process simply makes you more capable of making bad parts faster. So in order to avoid that, the best process we found is a brainstorming and concept development phase. Brainstorming usually broken up into a number of rounds. We kind of have an anything goes round where Anything and everything is recorded as a possible solution. No idea is a bad idea at this stage. Anything goes. Then we enter kind of an editing round where we remove the bad or infeasible solutions. This is usually dictated by the data you collected and analyzed in the previous stages. Then you start to bring the customer into it. So those first initial rounds are internal. You try to keep it with a small group. Then you bring the customer into it so they don't see all your bad ideas. We have some collaborative brainstorming with the customer, whittle down the options to a select few and say, these are the ones that we want to either investigate for research or enter the pricing phase. And during these phases, we're asking, some pretty standard questions. What are all the possible ways to make the part or the assembly? What steps in the process can be automated and which should be automated? If it can't be fully automated, is there a semi-automatic halfway there solution? If there's not a good automation case, can we give the operator some tools to make their job produce more quality parts, make it more ergonomically friendly, or just push throughput up? So we've taken all our conceivable automation solutions, we've whittled them down to solutions that fit within our framework. The next step is concept development. There's a ton of tools you can use here, depending on what the customer is comfortable with. We typically do 2D and 3D layouts. We place the equipment in the defined sandbox that we were given during collection. How does it fit in the space? Did we miss something during data analysis or brainstorming that may cause potential issues now that we're looking at it in a 3D model? We can investigate potential robotic solutions via robot reach studies or cycle time studies. We can do discrete event analyses to make sure that we're hitting the required throughput. Things of that nature are going to naturally eliminate some of the infeasible solutions that we had come up with. And here we would, again, we're wrapping everything around that data framework that we had created through our data collection, data analysis phase. And then for certain projects, if a process or part design is required, it may make sense to do what's called a design for manufacturing or a design for assembly. So when manufacturing individual parts, a DFM is going to basically be a deep dive into the design of that part and how we could potentially redesign the part to make any resulting automation less complex. How would we make it easier for a robot to grasp? Can we change the material to make it a simpler process? Again, the data collection, data analysis are going to set up parameters for what those possible potential changes are and whether they're going to be acceptable to the customer. When we're dealing with a collection of parts and actually assembling them, we would do what's called a design for assembly. Instead of changing the unique parts to make them easier to manufacture, we'd be adding things like tabs or things that make them easier to put together into an assembly. We could rework tolerance requirements, tweak the shape of a part to make it easier for automation to assemble it. Just a couple of specific examples for redesigning the part or the assembly around the process or the automation that we'd be proposing. So again, at this point, if we're left with multiple potential solutions that all meet our data framework, our requirements, our parameters, how do we make a solution when we're left with multiple possible solutions? So again, best idea is to let the data take the lead. Typically, we would put together a decision analysis matrix that puts each of the potential solutions against those prioritized goals and targets from our data collection visit that came directly from the customer. And then depending on what the customer told you is important, some of those solutions may naturally rise or sink below the others. Again, what is important to the customer is going to usually be the deciding factor. Sometimes that is a business case. Other times it's something as simple as footprint requirements or labor requirements. But ultimately, the goal should be to remove the emotions and the subjective feelings from that decision-making process and make it as objective as possible. And typically what we would do for any of our solutions is a business case. And the simplest way to do that is just calculating the return on investment or the payback. If that doesn't come from the customer, we typically would wrap that around a throughput increase or a labor reduction. Before I hand it over to Kevin, I did want to make a quick note on a few ways that automation is beginning to catch up to what would typically remain manual processes even after going through this assessment process here. The main thing is machines are starting to catch up to humans. Artificial intelligence, machine learning are starting to optimize things like machine vision, random part handling, data monitoring, predictive maintenance, plug and play user interfaces, and technologies that are making it easier for non-programmers to program. So these are all areas that are starting to move in from that R&D, research and development sphere into proven and in production solutions. So I'm going to pass over to my co-presenter Kevin at this point. He has a slide that goes into a little bit more detail here.
Thanks, Chris. So real quick, I'm Kevin Tom, engineer at eTech Group, and we're a system integrator. So let me take a moment here to share with you some of the challenges that we system integrators often face when automating a process. There's a saying that always comes to mind for me when I think of new plant construction. Automation always comes last. It's only after everything else is put in place that the integrator is brought in to install and test the control system. So they're often the last member of the team left on site. Integrators are often left to deal with tying up loose ends when things don't work. And worst of all, sometimes we have to deal with major flaws in the process design. What's a system integrator to do when they encounter a conflict between the process design that's left to them and the practical operation of the control system? Unfortunately, the reality is there's no one-size-fits-all solution. Sometimes it means going back to the drawing board and redesigning the affected parts of the process, like Chris mentioned. And other times, it's up to the system integrator to bridge the gap, modify the control system in the field to work around the blind spot in the original design. Now, before I go over a case study that illustrates some of these challenges, we're going to jump back to Chris to review some preparations for an automation implementation.
Thanks, Kevin. So I've got a couple more slides before I push it right back over to Kevin for his case study. I did want to reiterate a few of my main points that are going to be very important prior to kind of launching into that automation implementation. Number one being, I can't emphasize enough how important it is to start with the data and agree on the framework of that data to support any decisions that need to be made along the way. Final step being, a business case or an ROI perspective on that potential automation solution. Reduction of labor requirements and or increased throughput, whether that's via making more parts or the overall quality of the parts being made. Once a solution has been identified as feasible, has a good business case, and all the stakeholders are comfortable moving forward, the detailed project management plan can be created and the project then moves into the execution phase. So again, I'm gonna pass it back over to Kevin here, who has a great case study in automation implementation. So take it away, Kevin.
Thanks, Chris. So I'd like to discuss a case study in automation implementation where the system integrator was tasked with modifying a control system in the field to work around a blind spot in the original process design. So here's a quick introduction of the high-level process. So it was a pilot plant for a large pharmaceutical company. So you can imagine a lot of clean rooms and a lot of stainless steel like depicted here. The part of the process of interest was the suite of reactor tanks. Each had a dedicated temperature control unit, or TCU, that took care of basic warming and cooling. But when extremely low temperatures were called for, like temperatures below -30 degrees Celsius, the heat transfer fluid gets circulated through a liquid nitrogen or LN2 heat exchanger to get things really cold, up to, I think, -78 degrees Celsius. So here's a simple diagram to illustrate what's going on here. So starting from the left side, you have the heat transfer fluid coming in from the supply, goes into a TCU pump, which goes into the reactor tank jacket. That brings you all your heating and cooling, and then the heat transfer fluid goes back to the distribution through the return. So this is the setup when we're not thinking about LN2 cooling. But once an operator puts in a set point, something like -30, -40 degrees Celsius, that what we're seeing is everything here with the flow path with the LN2. So this is the same diagram we just saw, but if you see below, we have the flow path that goes into the heat exchanger as well as some extra valves. So same thing, starting from the left, you have the heat transfer fluid coming in from the supply and the pump, but now we have a path that goes downwards, and that's where you reach these valves here, this TCU LN2 supply valve, and on the return side, you'll have this return valve as well. These open once you activate LN2 cooling. And then we get to the LN2 heat exchanger, which is where all that extreme cooling happens with LN2. And then finally, we get back up to the top with the reactor tank jacket. And the amount of fluid that actually gets pushed down into the heat exchanger is controlled by this control up here at the top. So the more that control valve is open, the more fluid goes directly into the reactor tank jacket. And the more that's closed, the more it gets pushed into the LN2 heat exchanger. So again, this is the same diagram, but we just added on the nitrogen flow path at the bottom here. So down at the bottom left, you have the LN2 supply and the LN2 supply valve. So that valve opens up once LN2 cooling is activated. Next, you have the LN2 control valve here. This valve gets modulated based on the amount of cooling we need, and that gets determined by the cascade control loop here, whose PVs are looking at the temperature. The temperature is coming out of the LN2 heat exchanger, both on the nitrogen side on the top and on the heat transfer fluid side on the bottom. So after the heat transfer fluid goes to the LN2 heat exchanger, I'm sorry, not the heat transfer fluid. Once the liquid nitrogen goes to the heat exchanger, it comes out as nitrogen gas and comes out through the exhaust. So what's the problem here? What we're having going on was the system only worked for the colder TCU set points around like -60, -70 degrees Celsius, but not at the warmer TCU set points around -30 to -40 degrees Celsius. But what happened is that we figured out that the key flaw was we had that TCU control valve at the top of the screen we saw earlier. That was essentially acting like a bypass valve. So if there was the LN2 side, you had it very cold, and you didn't want something really cold coming into your actual jacket loop at the reactor side, then the TCU control valve gets really driven to open up a lot because there's that huge differential between the temperatures. And once that happens, all the flow is going from that TCU pump you saw, and it goes straight into the reactor jacket, and it doesn't go down that path to the LN2 heat exchanger. So what you ended up with is a low flow condition there, which eventually leads to freezing of the little amount of heat transfer fluid left in the exchanger. And once things start turning solid for a process like this, then you lose all ability to control the system. So let me explain that with the diagram we have here. So up here at the top, you see this TCU control valve. If it's opening a lot more to allow more fluid to go directly to the reactor tank jacket, then most of the flow is going that way. And we have very little flow that goes the downward path to the heat exchanger. So eventually that little amount of heat transfer fluid gets overwhelmed by all the liquid nitrogen in the heat exchanger, causing tons of freezing down there. So what we identified as the root cause for all this was simply that bypass valve was paired up with a piece of equipment that's really sensitive to low flow rates. But the problem was we were pretty much at the end of the project here. Things were almost all commissioned. And so the customer was coming to us and asking, how do we solve this problem using automation? How do we solve this problem without changing anything we've got in the actual process? So our approach was to look at that temperature differential between the LN2 and TCU sides. What was the difference between those LN2 and TCU set points that was causing that TCU control valve to open so much? So what we first observed was that LN2 set point down at the bottom gets set to a static -78 degrees Celsius per the design engineers. It was fixed, and it seems like, well, if you're going to set a set point at the TCU side to something like -30, -40 degrees Celsius, you're going to have this huge differential of like 30, 40 degrees Celsius. So of course, you're going to be working that TCU control valve really hard and opening it like crazy. So what we found was we need to find a way to decrease that differential. And the way we thought of at first was, let's use a fixed offset between the two set points. So that's the LN2 set point is something adjustable and it moves with the TCU set point. So after a little bit of sleuthing, we found that, let's say the set point offset of 5 degrees Celsius worked for a given TCU. So if the operator sets the TCU set point to something like -50 degrees Celsius, for example, then what we're going to do on the automation side is we're going to send a set point of -55 degrees Celsius to the LN2 side. All right, so here is a diagram to explain kind of what I'm talking about here. So first, I just want to clarify what we're talking about when we say the TCU set point. So what I mean here is the set point for the temperature of the heat transfer fluid that's about to enter the reactor tank jacket. And when I say LN2 set point, it's actually a bit of a misnomer, because what I mean is not the temperature of the LN2, but the temperature of the heat transfer fluid as it exits the LN2 heat exchanger. All right, so once we implemented this set point offset, keeping the LN2 set point a lot closer to the TCU set point, so the offset was much smaller, what we found was the TCU control valve didn't have to work so hard, didn't have to open up so much. In fact, most of the time it was closed, and it allowed almost all of the flow to go straight down to the LN2 heat exchanger, and we avoided that whole situation with the low flow and the freezing. Yeah, so everything was great, except when we went back to using those testing with the colder set points like -60, -70 degrees Celsius, we found that now we're not able to actually reach set point anymore. We observed that the colder TCU set points required an even colder LN2 set point. What I mean by that is so maybe at -30, 40 degrees Celsius, that offset of like 5 degrees Celsius worked really well. But once we got up to -60, -70 degrees Celsius, we need an offset of like 8 or 9 degrees. So the LN2 was much colder. So what we found was that the fixed set point offset just simply was too limiting. It wasn't able to account for this other factor. So I think we're sort of stuck between like a rock and a hard place here. On the one hand, you had that warm TCU set point scenario we talked about, where if this offset between the TCU and LN2 sides is too big, then we have all the flow going in the direction straight into the reactor tank jacket, not enough flow going into the heat exchanger, and we got all this freezing. But on the other hand, if that offset is not big enough, then we have the temperature down at the LN2 side is not cold enough to actually get us to reach set point when we get into the reactor tank jacket. So it seemed what the fixed set offset model was missing was that it wasn't varied based on the value of the TCU set point. So what we started wondering was, does the set point offset vary constantly with TCU set point? Or in other words, does the set point offset vary linearly with TCU set point? When we applied a linear model, we found that we were able to reach and maintain control at both the warmer and colder TCU set points. But for the TCU set points in between, we'd end up with a low flow condition and freezing again. Based on this and the data we were seeing, it seemed like perhaps it was the rate of set point offset change that was varying constantly with TCU set point. Or in other words, perhaps the set point offset varied quadratically with TCU set point. And when we applied the quadratic model, we found we were successful. We were able to control temperature across the entire set point range. So let me show you what this Goldilocks scenario looked like in the diagram. So essentially what we had going on was for the TCU control valve at the top, we were making sure it was more closed. It wasn't opening too much. So in order to do that, you had to make sure that your offset between the TCU and LN2 side wasn't too big. So this kept all the flow going down into the heat exchanger. At the same time, you had to make sure that your set point offset was big enough so that you were cold enough on the LN2 side to actually reach set point on the TCU side. So here's a little conceptual graph illustrating the different methods of set point offset tracking we use to model that relationship. So the highlighted region represents the Goldilocks zone in which temperature control is actually possible. In the area above the highlighted region, that's where the LN2 set point was just too cold. That offset was too big, and so we're seeing all of the low flow condition and the freezing happening. And in the area below the Goldilocks zone, what we were seeing was we just couldn't actually reach set point at the TCU. We just weren't getting enough cooling. The offset was too small. So if we take a look at the fixed offset method that's there in blue, it seemed to really perform well in the warmer TCU set point range. But we noticed at the colder TCU set points, there's insufficient cooling to actually reach set point. When you take a look at the red, the linear offset method, it worked well at the warmest and the coldest TCU temperature set points. But in that middle range, the heat transfer fluid would eventually freeze. We just couldn't really reach like a stable condition. And ultimately, the quadratic offset method you see in black, that's what performed the best. It allowed for TCU control to control the temperature across all set points across the entire LN2 set point range. So at the end of the project, I feel like we were able to build a lot of increased flexibility and functionality into the control system to patch around that design hole. But at what cost? It took a lot of testing, weeks and weeks of testing to figure out all this data and to figure out what model worked best. And there was a lot of delays in schedule. We were like the main focus of the whole project because we were holding everything up. And so things got pushed out a lot, and we spent a lot of resources, both engineering and management resources, as well as a lot of LN2. So what were our main takeaways from all this? I think what we really learned was that thorough initial design and investigation is really key. It helps avoid those scheduled delays and that frenzied rush at the end to fix everything. Essentially, that really saves you a ton of money, time, and headaches. We also learned it's really important to invite the integrator or the automation team into the conversation early on in the design phase. Essentially, that improves the effectiveness of that initial design and investigation phase. Integrators have seen a lot and likely seen a similar process from other plants. And the last thing we learned was that automation can do a lot, but it really can't fix everything. In this case, I would say it worked out well in the end. Automation isn't always able to fix the shortcomings in design. Sometimes it's more of a bandage than a real fix. But like was mentioned earlier, the earlier automation is brought in, the more effective automation can be, and the more likely the end user will have a system that they're happy with. All right, and that's all from me in my case study. So now back to Mark for the Q&A session.
Thank you both. Nicely done. The audience listening live can continue to type questions for today's presenters in the Ask a Question box on the screen. We'll get to as many questions as we can. And then within a few days, the presentation will be available for on-demand viewing, along with the link to the quiz for potential PDH credit. We'll post the archive on the Control Engineering website, and then we'll send an email message with the link connecting directly to it and to related resources after it's ready. So now on to the questions. So we know we need a system integrator to help with a major upcoming automation project. When should the integrator be brought in, ideally?
That's easy from my perspective. Is the earlier, the better. As long as everyone can be on the same page from day one, you're going to deal with a lot less headaches down the road.
I think especially if you've already identified that this is an automation project, I think you already know that automation is needed. It's great to bring automation in as early in on the design phase as you can. Great. Great.
In the case study presented, what was the relationship between the set point offsets quadratic in nature?
Yeah, not necessarily.
Yeah, so was the relationship between the set point offsets quadratic in nature? Yeah.
Right. I think for all we know, the relationship was something more exponential or cubic or something else. The quadratic model was just that. It was a model. We based it on empirical data that we gathered through running system many, many times to understand the relationship between those two set points.
And then also in the case study, what process was used for determining which model worked best?
So that was a lot of trial and error. We'd run those TCUs with LM2 cooling with the varying set point offsets, as well as the varying set points themselves. Every time we ran a test, though, it'd take hours and hours for the sequence to initiate, and it'd take us several more hours to feel confident that, yeah, we'd reach set point stably. We're constantly running out of liquid nitrogen, and we had to call for refills from the vendor almost daily. And once we finally got some data about what set point offsets worked for what set points, we had to determine which model fit the data best. Now, early on, it looked like the linear model would work, but one of the confounding factors in all this was that for each of the TCU to LM2 heat exchanger pairs, they had a different correlation profile. So though the linear model was working for some of them, we opted to use the quadratic model both for consistency. And once we got more data, we found that it worked well in all cases.
So switching back to discrete automation, would you target the highest volume part number, the most profitable, as opposed to the entire product line, or the process most easily to automate to gain buy-in by management? How do you choose?
So I think the initial that goal setting or target setting process early on during your data collection phase, that's where you need to get on the same page with management. You tend to get a good idea of kind of what their appetite is for automation. A lot of times, especially if it's a smaller company just dipping their toes in again, they may want to go with a small cell somewhere out of the way, not necessarily right in the middle of their production floor, that they can use to test or kind of get comfortable with automation. And typically that would work on maybe the more profitable part, if the idea is, hey, if this small test cell is successful, let's blow it up into an actual full size production cell. So again, I think it depends on management. You can go any one of those ways. Some companies are gung-ho. They want to automate no matter what. So you target the highest volume part number and try to get as much of that product mix in the automation as possible.
Kevin, does the same thing apply to the process area?
Yeah, I would say that's true too. Yeah, I don't think there would be a difference there between discrete and process sides for that.
Great, thanks. So in your opinion, what's generally the most overlooked return from implementing an automation solution?
In my mind, that's people. Sometimes automation or robotics gets a bad rap for stealing jobs or taking humans' jobs away. In my experience, from my perspective, robots are freeing up the human potential to do what humans are good at, and that's use their brain and think and be creative. It's not to sit in on an automation line necessarily and do repetitive tasks. That's what automation is for. So the freeing up of human capital, ingenuity, creativity, that is by far the biggest return outside of the monetary, typical payback that you'll get from automation.
And Kevin, on the case study, if automation had been involved earlier, what might they have said to avoid the design flaws that were seen later?
We've seen similar situations before, and I think we could have provided more of that control systems operations perspective on this part of the design. Like one solution maybe we could have proposed is to get rid of that TCU bypass valve and have the TCU control the LN2 control valve directly. And this would be like a much simpler design without that risk of creating that low flow condition and the freezing. But the limitation of this is that you can't simultaneously provide multiple TCUs with LN2 cooling from the same heat exchanger. But I guess an important question that you'd want to ask your end user is, how often is that actually needed? Does the need for that actually outweigh the design, materials, installation, and automation costs associated with creating that functionality? But if that's the case, you might want to consider designing more of an LN2 cooling distribution loop with drops for each TCU or something like that. Of course, that'll cost more because you'll need like a dedicated pump and additional control loops. So in the end, I think it's a balancing act of priorities. There's no one answer, but what's important is having that conversation to make sure that the customer is getting what they want in the end, a system that works and meets their needs.
Yeah. For a company that has little or no experience with automation, where should we start? Chris, maybe you want to take that one first, then Kevin?
Yeah, systems integrators are a great resource. Automation consultant. I may be biased, but that's kind of what I do as an automation consultant, is kind of guide customer or client through that process of collaboratively figuring out whether or not automation makes sense. So I'd start either of those places.
Yeah, I think that's totally right. We've seen a lot of companies that don't have an automation department. They don't have any automation engineers on staff. And so they come to us and say, help us build a URS. Help us figure out what it is that we want and what we need. And we've seen so many of these. We are really good at helping collaborate and figure out what it is the customer really needs to automate and what parts are not as important.
Good. We have time for one more question, but audience members, please continue to type in more questions for these experts. We'll get to them offline and make it available with the archive. So go ahead and keep typing in your question and we'll get to one more. Let's see. So what are some of the challenges that come up when upgrading older, or aged, or obsolete automation systems?
I think reliability would probably land at the top of that list. Obviously, older systems have a tendency to break down, have older parts, and potentially parts or replacement parts that are harder to find. So potentially more expensive just maintaining that system in the long run. But again, that entirely depends on what type of automation and how old it is. But that's the most frequent problem I see with the older systems.
I think my take on this would be, a lot of times you walk in and you have these older, obsolete automation systems, and the customer wants to upgrade to something that's very similar. But at this point, there's nothing similar left. There's no more replacement parts, and there's nothing that you could have like a one-to-one kind of relationship just to move over the software onto new hardware. And so what you end up having to do is, really understand everything about their system and look through all their documentation so that you can do your best and cross your fingers that everything will work out when you move over. And that requires a lot of testing to make sure that everything still works the same and everything is still qualified.
Well, thanks to our audience for the great questions. We'll try to get to as many of the unanswered questions offline as we can. And thanks again to our presenters for their insights and answers. Chris Clayton, Advanced Manufacturing Engineer, Applied Manufacturing Technologies, and Kevin Tom, Lead Automation Engineer, eTech Group. And we want to thank again to our sponsors, and Maverick Technologies, Mitsubishi Electric, and Schneider Electric. And now that we're just about done, please, everyone provide some feedback. A short survey will pop up on the screen as soon as the webcast event ends. Take a moment to complete it. We'll use this information to improve future webcasts. Finally, on behalf of Control Engineering, CFE Media Technology, and our speakers today, thank you for attending. This concludes our webcast. Thank you and goodbye.